All right, so perhaps in the same spirit, what is it that controls the duration of immunity?
I think there's a lot of people who would like to know the answer to that question.
That's why I'm asking, so here's your chance.
Vaccine developers.
So it's a really interesting, it's a tremendous problem, really. And you just need to look at the natural history of infections to get a handle on where we actually can elicit good long-term immunity. And so a subset of us here had all those childhood infections because there weren't vaccines. There weren't vaccines available for things like chickenpox and measles and mumps when a subset of us were children. And we became infected and never got infected again. That is a good indication that there is an opportunity to use vaccination to elicit long-term immunity. Okay, so we need to go to the natural situation. And then what about all of those things that we get infected with every year? And there's a series of GI tract infections and certainly the 40 viruses that cause the common cold. We have no vaccines for those, and they don't elicit good protection. So the features that dictate the long-term immunity, first of all, we have to have, gotta have the right environment for those cells to form. You've got to have the cells proliferate correctly. You have to have the correct signals for the cells to not die after they've undergone this major expansion during the infection. So there's a number of steps there, and all of those have to go right. I think we started earlier saying it's biology. Nothing ever goes right in biology. So there's a number of steps where things can go wrong in different infections, and certainly the pathogens that we're talking about can manipulate these steps. Okay, and we don't know exactly where those steps, you know, how you can manipulate to prevent those memories, those key memory cells from becoming long-lived. So let's say all of that goes quite well, and then you come around with another virus, and this could be a herpes virus, it could be HIV, that kills those cells off. So everything went right, but then something knocks off the cells. It doesn't have to be an infectious agent, it can be a toxic insult, okay, that just by chance kills those cells off. And so now you don't have those memory cells anymore. Okay, so there's multiple factors, and you know, we can work it out maybe for one infection agent, but it's very difficult to generalize, I think.
Because I think it's just fascinating. I obviously don't I work in the population end of things, so think about epidemiology. But actually the kind of equivalent, I find it deeply fascinating, the equivalent demographics of maintaining that population of memory immune cells, because so they have to, so they pretty much divide about twice a month or something like that. So,
it depends.
And then one of the daughter cells is gonna disappear or something because you want to keep it homeostatically controlled at a certain abundance, and then you're gonna manage to do this month after month after month, year after year, and manage to sustain the population to maintain that memory for a lifetime. It's just baffling.
It is interesting. We're getting to the point now where we have tools, genetic tools, where we can genetically mark those cells, and we'll have a better ability then to track the fates. Mm-hmm. You know, whether or not they simply didn't form, whether or not they aren't getting the signals to survive, whether something has come around to kill them, whether there's new aspects of biology that will cause those cells to revert to another state. We don't have evidence for that, but as I said, it's biology, it probably happens.
I think too that, to me, one of the big open questions, when I get any question answered, one of mine would be, why is it that there are some diseases which we call acute childhood infectious diseases, precisely because they specialise on fully susceptible individuals? And despite intense selection during those collapsing population waves for any mutant that could persist, get into a person who's just seen one, they can't do it. And yet it's clear that other pathogens can do that. It's an incredible Why is that? Why is measles so hopeless from an evolutionary perspective? Why can it not come up with some way of getting into semi-immune people?
Yeah, it's baffling because I know also.
Well,
this
don't
might-
you work on measles?
Well, so this is getting kind of this. I guess this is getting kind of technical, but I know. So apparently, if you challenge the virus with monoclonal antibodies, then the virus can evolve around it.
Uh-huh.
So in a petri dish, the virus can find ways to get away from at least a specific set of antibodies. But you stick it into a mammal, whether it's measles in humans or Foci distemper virus or rinderpest or whatever, they just can't manage to escape that immunity.
It's still with us.
That's
It's not that it's not a successful virus.
Right, but it's still the case that any virion that could do it would have a huge selective advantage. It should be able to add on, and there are clearly many pathogens that can do that. It's very somebody should figure that out.
Well,
Nobel
I mean,
Prize then.
what are the hypotheses? Is it absolutely
Well,
no
actually,
one-
I think most of the sensible hypotheses, like Otto says, there's evidence against them, and so there's nothing wrong with the rate of evolution. It does everything in a normal kind of way. Other genes in that genome evolve just sensibly. Everything happens properly.
Does that have anything to do with our relatively recent history with measles and other crowd diseases? Haven't they oftentimes been thought to come about because of the formation of cities and having larger?
I'm not going to let you have that.
It's just a question.
Just even if big groups of people have only been around for a few thousand years, that's a ton of virus evolution. I mean, there's a ton of virus evolution and rinderpest and all those other things. Can I understand?
So it's got to be a
You can't
trade-off
have
with
that.
something else, doesn't there?
Yeah.
I mean, that's the answer at the end of the day. It's got to be a trade-off. But is that on transmission? If that's on transmission of measles, then there could be, if you're going to reduce your transmissibility in some sort of way.
Yeah, I mean, my understanding was that one of the primary hypotheses, at least for measles and the other morbillivirus, is that the specific conformation of the antigens that are presented on the outside of the virus are essential for the mechanism of getting into and getting out of the cell, and it's that specific conformation that has to be really highly conserved in order for this thing to be able to do its business to facilitate transmission, and that any minor changes from that, which might help it escape the immune system, have such a strong and severe cost in terms of the ability to colonize cells and then get back out of them. That in fact you might gain a great benefit by escaping the immune system, but you would necessarily lose fitness as a consequence of not being able to transmit.
It must be something like that, but that sort of suggests that what's happened is the virus has got itself parked into a bit of perimeter space where it's absolutely impossible to get moving. Because lots of other viruses and lots of other pathogens haven't got themselves stuck into specialising on fully susceptible individuals.
Have we learned anything from the phylogenetic positions of these viruses? Are some which are parked in this parameter space in one group compared to another, or do we even know what groups viruses are in?
Yeah, I mean, they're in the Paramyxoviridae, and they have 3-4 families that are responsible for the common cold, for which we have no immunity and no good vaccines. They're highly diverse virus families in all of them. I mean, the morbilliviruses are a highly diverse virus family. Canine distemper virus is quite good at evolving around. Well, that's a difficult question because vaccine breakthroughs can occur because of improper use of the vaccine. So it's hard to say whether or not that if vaccinated individuals become infected, whether or not they were actually effectively vaccinated.
But canine distemper virus occurs in multiple host species, while measles is essentially a human infection, isn't it? So
As
it's
far
very
as we know.
different.
Yeah, but it's interesting given the level of vaccination and general immunity that virus is still, it is ready to go.
Yeah.
And we have, viruses don't persist in the environment. It's
when you
staying
mean
in.
ready to go, when it finds a susceptible.
That's right.
Yeah.
And we've seen, I mean, there's been some really good outbreaks. Ottar can probably, elaborate on this, but, in small groups that don't vaccinate their children. There was an outbreak in Boston, 3 or 4 years ago, or
Not
a
you.
partial vaccine?
for measles.
Yeah.
Oh, I mean,
There's
there's
multiple.
no shortage of, yeah. I mean,
This
there's
is
been,
in the U.S. where
yeah. I mean, there have been
Yeah.
there are dozens of small outbreaks in the U.S. in any given year, and
Right.
as well, there's been massive resurgence in highly vaccinated populations around the world. I mean, France 2 years ago
That's right.
had tens of thousands of cases of measles. Germany last year thousands of cases, and the same in large parts of sub-Saharan Africa, where vaccination has done a very good job of reducing transmission and effectively eliminating things. But the susceptible population creeps back up as you get some people that aren't vaccinated in any given year, and you get these massive outbreaks that sweep back through. So it's a tenacious virus, and it's absolutely waiting at the ready to reinvade populations.
And I mean, you're touching on a couple of questions that we'll talk about in future weeks as well. I mean, population dynamic processes and vaccination.
Yeah.